This conference will now be recorded.
So, Chitra,
Yes, ma'am.
what are the types of drug excipient interaction we have just completed last class?
Yes, ma'am. Chemical interaction we completed,
Huh. That's all?
and deliberately designed interaction.
Okay, that's also good. And actually, we completed the
Uh,
excipient interaction, both physical and the chemical interaction.
Chemical. Yes, ma'am.
Okay, so physical and chemical. So today we'll be proceeding with the
Yes, ma'am.
next part of the topic. You can mute yourself. So today we'll be discussing about the methods. See, I was telling you drug excipient interaction are of varieties, okay, based on the nature of the polymer and sorry, that is excipient and the nature of the drug. We can expect varieties of drug interaction can happen, but broadly it can be categorized into physical interaction and chemical interaction. Fine. So these interactions are not visible every time. Some interactions are visible, like any obvious change happens with the physical properties of the drug, which is visually you can see that. Color change, for example, that can be visualized and you can say drug interaction is happening. But not every time that you can assess the drug interaction, or assess in the sense it can be qualitative or quantitative. Even qualitatively, you cannot say that the drug interaction has happened. So there should be some analytical method. So we depend so much on the analytical procedure techniques that helps us to determine the drug excipient interactions. So that's what I'll be covering today, the topic, the methods of evaluation of the drug excipient interaction. Doesn't matter it's a chemical interaction or the physical interactions. So now when you look at the chemical interaction, so this chemical interaction is mainly with respect to the chemical changes which happens when the drug interacts with the excipient. So the safety profile of API, that is active pharmaceutical ingredient, is established before the pre-formulation work. Correct. So that is what the characterization we do. So there is a possibility we know till now already we understood that the drug excipient reaction might produce a new component. Means there are many things can happen when the drug interacts with the excipient. There is a result that the new impurity might form. And this new identification of this new impurity is also challenging for us, and that new impurity is nothing but an indication of the degradation of the drug and the excipient. It may be the drug is getting whatever the drug is interacting the excipient means definitely there is a degradation happening. So identifying this becomes very important. So frequently what we do is we depend on analytical technique like the chemical composition. We need to determine the chemical composition. So one of the method to say whether it's been the API is in its normal state or it's been altered. So some of the techniques what we can use is the TLC, that is the chromatographic techniques, HPLC techniques, and even the MS, mass spectrometric techniques. Okay, and also sometimes we also can also use other spectrometric analysis technique also like UV, FTR, and also other than that NMR also. Okay, so all this analytical technique, whatever you would have studied in your, and I mean, which you will be studying actually in detail in the analysis subject, which is a modern pharmaceutical analysis subject. So please understand that we are not discussing in detail all these equipments. That's not our part of the subject. We're actually understanding how it is used for our need. That is how the drug and excipient interaction can be identified when we use using this different analytical techniques. Its construction or its working or its applications, its advantages, disadvantages, all this you'll be learning detail in the analysis subject. So we'll be learning about the different techniques. So in that techniques, you can categorize into varieties. Spectrometric techniques I can call it as, or I can call it as a chromatographic techniques. Means the analytical methods, whatever you adopt, can be grouped based on the basic concepts. When I say spectrometric method, for example, the first thing comes to our mind is like colorimetry method or UV spectrophotometric method. All this based on the spectrum. Okay, that's why it's called a spectrometric method. Similarly, when I say chromatographic technique, all this HPLC, TLC, all that comes under chromatographic technique. Same way here, There are also some other techniques can be categorized, like analytical technique based on thermal decomposition or based on thermal processing. So, and this thermal, the analytical technique which is running based on the thermal concept, no, they have major application in identifying the drug excipient interactions. So, thermal decomposition or volatilization process, nothing but. You don't worry of much in. We are not going in depth. That's what I was telling you. Superficially, you are trying to understand, but still, you should have the knowledge how these analytical techniques are used for our need. So some of the analytical techniques, what is you can study, which is their part of your syllabus, or which I feel is important for your syllabus. Syllabus would have not mentioned this technique names. They would have just given, they have given just the analytical techniques. So DSC, okay, differential scanning calorimetry method. MDSC, modulated DSC, is a slightly modified one that's called as a modulated DSC. And thermal gravimetric analysis method, hot stage microscopic method. All these are some of the techniques or analytical techniques which is based on the thermal processing or based on the concept of thermal decomposition. Fine. So we'll be learning in detail, and some of them are major one I'll be discussing is the DSC, differential scanning calorimetry. I repeat, it is called as differential scanning calorimetric technique. So in this technique, the one of the important parameter which you have to understand is something called as TG. That's called as a glass transition temperature, TG. If at all you have learned, remember you have, I think somewhere you would have learned about the polymer. I'm not very sure where this TG value is very important for us. So glass transition temperature, when you subject any material to the higher temperature or thermal procedure from high to lower to higher temperature, how the change happens to that material. And one of the change is called as the glass transition temperature. And it is a temperature below which molecular mobility means. Imagine a temperature now 150 degrees centigrade. It's a glass transition temperature of any one drug. Let's imagine. It's just an imaginary number I'm giving you. So below that 150 degrees centigrade, that is below which the molecular mobility of a glass amorphous solid is dramatically reduced. Means glassy amorphous solid is dramatically reduced, and above which the amorphous material takes on a rubbery characteristics. The consistency, the texture will change, which increase in the number and molecular motion. So it's something like you can imagine like solid is converted slightly into rubbery texture. So there is a texture. I'm just as an imaginary terms. I'm just making you understand with the imaginary terms also in the sense solid to the not liquid exactly. It is a rubbery texture. So what happens when it converts into rubbery texture? The mobility of the molecules which are present in that chemical, no, it will be high. It have more chances of moving around. So increased mobility can lead to increased chemical reactivity. This point you have to remember. Increased mobility lead to increased reactivity. It gets more opportunity to interact with another molecule and result in the interactions. So generally what happens is amorphous material can change into crystalline form when you keep it for a longer period of time at particular temperature. So now this information is need to be we need to understand this information because that helps me to decide with the temperature of the storage. At what temperature I can store this now, this API or the drug and API mixture, whatever it might be. Knowing the fact that above this temperature, that is called as a glass transition temperature, the mobility, there is a transition which happens because of which mobility of the molecule will increase, and because of the increase in the mobility, there is a chance that the interaction can happen. So, okay, that is one thing. Here, the amorphous, whatever example right now you're seeing in the slide, the amorphous compared to the crystalline, when we talk about the solubility property, amorphous has a good solubility property compared to the crystalline. So we need to make sure that the solubility is very important for us, especially when we deal with the APA molecules, because good solubility, definitely it will have a good bioavailability. For any drug to have the required bioavailability, the so-called bioavailability rate and extent of drug reaching the systemic circulation. For a drug to have a good bioavailability, the one property it should have is good solubility. So that's the reason we always look at the property called as aqueous solubility of the API molecule. So you better, if you know already the drug is in the amorphous state, definitely it will have a good solubility. But taken care the temperature of its storage, then what you can achieve is you can avoid the drug converted into crystalline form, which is happening because of change in the environmental factor. The change in environmental factors is mainly the change in the temperature of storage condition. So any change happens surrounding that drug molecule can result in the transition. So storage temperature should be always less than the glass transition temperature. Keeping in the mind the advantages, below the glass transition temperature, the amorphous material cannot easily get converted into crystalline form. So, but above the glass transition temperature, there is a chance that there is a conversion and that results in the transformation and that results in the instability of the drug molecule. The same thing can apply even with the drug excipient interaction also. So DSC concept means helps us to assess many things, but one of the important parameter which you can determine is the glass transition temperature. That's one of the application I can call you right now. There are many applications of the that is differential scanning colorimetry method. One of the application is helps in determining the glass transition temperature designated by the letter TG, alphabet TG. Okay. So now, as I was telling you, DSC when you learn as a one of the analytical tool in the other subject, you'll be learning in detail. So superficially, I'm just giving you idea its application or its importance or its how for what all purpose we can use the DSC. So it helps in measuring the melting point. Of course, you must have done in the laboratory capillary method. Capillary tube method where we determine the melting point of the API, which is solid in nature, correct? Where you, that is fusion method you call it as. You heat it at higher temperature, note down the temperature at which it melts and you note on it as a melting point. Same melting point can be determined by another technique called as the DSC. So this DSC helps us to detect the melting point of the any substance, okay, and heat of fusion, latent heat of melting, reaction energy and temperature, glass transition temperature. Maybe, as I was telling, we are not going in detail. Even I'm not very well versed with this technique because we don't have in our college this. It's a quite expensive uh, equipment and maintenance cost is also very high. So we are not kept this. We don't have this equipment in our college, but we do depend on this DSC for many reasons, especially when you come to the second year research work, where you're doing some research work and there you want to identify any interaction has happened after you have done the formulation, then you need to send the sample for the DSC analysis. So the information on the DSC, whatever right now you are learning, don't think it's only for the purpose of first semester exam point of view. It is also helpful for us in the second year also. So the two things, the glass transition temperature, you got an idea with the explanation I just gave you. And another important parameter which you can determine with the DS is the melting temperature, that is the melting point of the drug. And also based on this melting temperature or the glass transition temperature, we can able to decide whether the drug and excipient interaction is happening or not. We can easily identify that also. Slowly I will let you know how it is done with some examples. So that's about the applications of the DSC. So now we are actually talking about what? We are talking about the thermal analytical techniques which is used for identifying the drug excipient interaction. In the thermal method, we have started with the DSC, differential scanning colorimetry technique. And DSC is mainly helps us to measure many of the parameters like melting point and the glass transition temperature, etc. And also it helps us to identify whether the drug is converted from amorphous state to crystalline state. Even that can be, that's called as a phase transition. This is called crystalline phase transition temperature. Okay. So, and also because of these parameters, we can easily identify whether the drug is getting interacted with the excipient or not, or any changes happening to the pure API also. If not just the interaction, even not only the interaction we can study, we can also understand anything is going wrong with the API or anything is going wrong only with the excipient. Are they sensitive to any particular environmental factor, or they interacting together and resulting any degradations? All this can be easily understood with the help of the thermal process, DSC techniques. So now what does it measures? The next question comes into our mind is, okay, we have an equipment called DSC. So, and we are subjecting our material for the analytical technique, that is DSC technique. And it measures what? It measures the amount of energy absorbed, because it's a thermal procedure where we are actually exposing the substance from lower temperature to the higher temperature. And during that process of low to high temperature, we are trying to measure what change or assess what change is happening. And that change is happening because of amount of energy absorbed or released by sample when it is heated or cooled. So it is a heating and cooling procedure. So providing, and this provides us quantitative and the qualitative data. So it can be used for both quantitative purpose as well as the qualitative purpose as well as the quantitative purpose. So this data, whatever you get, is called as endothermic data or the exothermic data. So endothermic is heat absorbed value and exothermic is heat evolved values. So like this, DAC helps us to measure the change with respect to measuring the or identify the change quantitatively as well as qualitatively by measuring the energy absorbed or energy released, and which that process is called as endothermic and exothermic process. So look at the graph now. This is how the graphical representation is done. So any analytical technique is represented in one or the other form, and one of the representation is a graphical representation, and this is called as endotherm graphs. So this graph has same that y-axis and x-axis, and x-axis is temperature and the y-axis is the delta T, and this delta T, if it is increases, it is called as exotherm. This is called as an exotherm if it is increasing, and if it is decreasing, it is called as endotherm. So this is called thermal representation. Okay, thermal representation of the DSC analysis, which contains x and y axis. And they ask you to write in exam. For example, in your question paper pattern, the 15 marks long answers will be there, the longest say. Next comes the 8 marks short essay, and next comes the 5 marks short answers. So this is how the pattern of your questions will be, like 15, 8 and 5. There will be no 2 marks questions in your case. Forget all the 2 marks, whatever you would have enjoyed in your UG level. In the PG level, this is what. So generally, they might combine all together as an interaction and analysis. Combined question can be a major. But interaction, on the analytical part, they will not ask you as a major question, like for the 15 marks. We can expect for the 8 marks and the 5 marks question. So you have to write about what is the analytical technique. For example, what is DSC? Write full form of the DSC. Then you write what is the application of the DSC. Then you write how it is represented graphically. Show one example of the graph as answer point, and then just try to go ahead as per the marks, 8 marks or 5 marks. So if it is part of 15 marks, it will be along with some other question, but not exclusively as the analytical techniques. If at all analytical techniques means all analytical techniques, by chance if you get 15 marks question also, you should talk about all the analytical techniques which I will be covering. In brief only you will be writing, but it depends on the question, the marks. But this is how the answer point should be written. So this is the graphical representation. That's what I was telling you. And look at this, how the graph comes. The peak increases or peak decreases. If it is increases, exothermic. If it decreases, endothermic process. So all this kind of changes. I have just given the two different examples here. Don't worry which is that drug, if nothing, you don't worry about what is that chemical or whatever it is. It is just a representation I want you guys to understand how it is represented. So this is how the peak, if the melting point peak comes, sharp endothermic peak. Okay, can you see the sharp endothermic peak? And this is called as a glass transition temperature. It means the line will just move smoothly parallel to the x-axis. That's called as a glass transition temperature. And by chance, if any changes happen, amorphous form is getting changed to crystalline, and suddenly the line will jump or increase like this. And that indicates, so looking at the graph, I can say, okay, some changes happen during the thermal procedure, and that increase in the peak towards the upper side indicates that there is a crystallization, or crystallization would have occurred. So it gives us an idea whether any changes happened to the API or not, or any changes happened to the API mixed with the excipient or not. Same with some of the process also can be identified with respect to the oxidation also. So again, I am telling you, it's not a very simple thing to understand in a 1 hour class. So a person should be an expert person in this particular equipment who can actually identify the changes happening, looking at the change in the thermogram. This is called as thermogram. Whatever the line you are seeing here, no, all these lines are nothing but called as a thermogram. So this graphical representation helps us to identify some of the important changes happening with respect to the sample subjected to the analysis. And the major one, very easy to identify, is, as I was telling you, is the melting point. It's a melting point. Sharp peak we are going to get indicates it's a melting point. And by chance the line is running without, after some time, without any variation in the peaks, either upper side or the lower side, that indicates it's a glass, it has crossed the glass transition temperature. So you can identify what is the glass transition temperature. Look at the advantage. So by this technique, I can say what is the glass transition temperature range. So what I do is I will keep that in mind by deciding about when I decide about the storage condition. Hope you understood now the advantage of knowing the glass transition temperature. DSC helps in identify the glass transition temperature, so that make me to decide what may be the storage condition, and also not only the storage condition, I am doing the formulation. Let me imagine I'm mixing the drug with the excipient and I am carrying out that particular temperature. The temperature is required for the formulation. Let me imagine. So I need to very carefully decide about that what temperature I need to carry out the formulation procedure. That temperature, does it affect the drug property? This kind of decision can be done with this thermal graphs. Okay, these are called as thermograms. So graph represented, the graphical representation of DSC are nothing but called as the thermograms, which is containing the x-axis temperature, y-axis containing the endothermic and the exothermic parameters. That is delta T. Okay. Any doubt?
Yes.
If we specific doubts, see, I'm telling you, we are not running in detail, don't worry. But at least got an idea what is that importance of running the analytical technique called DSC.
Yes, ma'am.
Okay, fine. So just in continuation with that. So now when I do, mainly we are looking, and we are learning this DSC with respect to drug excipient interaction, of course. So for example, when I want to understand the drug excipient interaction, how to proceed is the question. Okay, so what I have to do is I need to run the thermogram for the pure drug separately. Then I have to mix the drug and excipient physical mixture. That's called as a binary mixture. And again run the thermogram separately. Means I'm talking about planning of analysis, how it has to be done. Okay, not means we need to run the thermogram for the individual drug and individual excipients. If you really want to understand the interaction happening, first you run all the individual components like that API separately, excipient 1 separately, excipient 2 separately. Get a thermogram of all the drug, all the excipients along with the drug as a separate. Then you do the mixture of the drug and the excipient. Okay, in the ratio whatever, which I already gave you an idea. The ratio depends on the amount what we are adding to the formulation. So do the physical mixture of the drug and excipient. Again, you subject that to the DAC. So like this, you should have the different graphs with us. And then I need to compare. I need to compare the thermogram of the individual component is compared with the binary mixture of the drug excipient. Then only I can say the interaction is happening. Correct? If I directly mix the drug and excipient and then run the DSC, you might get the graph. There is no doubt in that. But how is it you're going to say that the interaction is happening? It's not, you cannot say unless until you compare that graph with the pure drug graph. So this interaction, if interaction occurs, what will happen? New thermal events are observed. New thermal events means what? Some change in that line, graphical line, okay, which deviates from the original thermogram. So if I have the pure drug thermogram and then the drug and excipient thermogram, I'll show you the next example. Maybe this makes you understand better. This is how. For example, this is a drug which they have used. Don't worry, what is the drug and all that means. So methimazole I've just taken from the internet source. So this is the pure drug. They have run the DSC curve and they observed the peak at 145. All these values are default, will be given in the thermogram. It depends on the equipment model. You can get all the details on this graph, even the delta T, heat of fusion, everything you will get, which is represented on it, like 149.2, whatever you're seeing here, no, there's nothing but that is delta, the H, that is, and heat of fusion it is called as. So this is the drug. So let's not worry about that, all that. So this is a drug, they have done the DSC separately, and again they have done the DSC separately for the physical mixture. PM stands for physical mixture of the drug with the some excipient. Don't worry what is that excipient. And look at the peak now. Compare the peak. This is the drug excipient peak and this is the pure drug peak. Do you see any change? What is the change you can see? Chandana, what is the change you can see in the peak, Chandana?
There is more in this thing, ma'am. The methimazole thing.
What more? What you use the word? Use the word. Let me see. Technical word. Keep thinking. Tejaswini. I want a word, a proper word. Asha, Ashita. Yeah, tell me a word to say what is the change you are seeing.
Ma'am, heat flow.
Who is speaking? I want it to be interactive. Soundarya is K.
Ma'am, melting point is increased in pure drug.
Melting point is increased, you want to say, dear?
Ma'am,
Melting point is?
melting point is increased in compared to excipient, ma'am.
Okay, let me look at the number here, 144.53 and 145. Do you think there's a difference? Did you see the number? I don't know if you're seeing in mobile, it's visible. Can you see this number here?
Yes, ma'am.
Yes,
Ah,
ma'am.
it's called intensity of the peak. So that's what, no? We need to use the proper term. You can see the change in the length of the peak in a normal layman language. If I tell all of you can mute yourself. You can see the length of the peak is changed. This is the length in case of pure drug and this is the length in case of, correct?
Yes, ma'am.
Okay, that's called as intensity
ma'am.
of the peak is reduced. You have to use the word, the peak intensity has been reduced. But do you see any change in the melting point either in the pure drug? Sorry, you know the pure drug melting point is somewhere near to 145.5. And same thing you could notice even in the physical mixture of when it is mixed with excipient, correct? The melting point has not changed. Yes or no?
Yes, ma'am.
Yes, ma'am.
Okay. That indicates that okay, melting point is not changed because they could observe the peak almost in the same position even when they mixed with the excipient, right? Even after mixing with excipient, they could see the position of the peak to be retained in the same position as 140 near to 145. But only observation they could see was there is a change in the intensity of the peak. The intensity of the peak is reduced in case of physical mixture, drug physical mixture. So this indicates that one thing we can conclude, interpretation or what we can do is, since the melting point is retained even after mixing with excipient, there is no interaction happening. Okay, the one thing I can say, Though the intensity of the peak is reduced, the melting point peak is in the same position. There's nothing would have happened to the drug when it is mixed with the excipient. The intensity would have reduced. Why the intensity of the drug is reduced? There may be many chance that the excipient would have formed a coating around the drug. There's a lot of things. Means that's what the interpretation depends on the what work we are doing. What is that excipient you're using? Depending on that, we have to do the interpretation. So interpretation is another challenging thing. Maybe in the analysis, that is what you also will be learning. May not be drug excipient interaction interpretation you'll be learning, but you'll be learning NMR interpretation, mass interpretation, means interpreting the result. Maybe the tool is with us, analytical technique we have instruments with us, but when we don't know how to interpret the result, it's waste. So a person should have the knowledge, a strong knowledge to interpret the result data, whatever you get out of that analytical technique. But this example, whatever I've given you right now, just to make you understand it, this is how you can do some interpretation with the help of the thermogram, which is obtained after subjecting the samples to the DSC analysis. Okay. So same one more example I've just added here. Next one, same here. As you can see, maybe the paracetamol, it sounds very familiar to you. That's why I took this graph. So paracetamol, the red color peak, they observed that its melting point is 170 degree, and they have mixed with the excipient called as PEG 4000 for preparation of narrow suspension, and they have taken the thermogram of the PEG also, and look at the PEG thermogram is coming somewhere at 60.7, and the paracetamol thermogram was somewhere at 170. This is what I was telling you. When you run the thermogram, you are running the thermogram for the pure drug also, you are running the thermogram for the individual excipients also. You get a better idea when you run, and then you do mixing of all, whatever the drug excipient interaction you want to understand. You can mix drug with the excipient 1, or you can mix drug with excipient 2, or you can mix drug with excipient 1 and 2 all together. What is that you want to learn, understand? See, accordingly the mixture has to be prepared and it is subjected to the thermal analysis. So in this graph, so they prepared the nano suspension, and this line, the first line, indicates the nano suspension, and that nano suspension was again subjected to thermal analysis, and they observed that there is no change in the melting point position of the paracetamol, which confirm that the drug is not degraded, or there is no change in the properties of the drug, or no interaction has happened, though the peak intensity is reduced. And also they noticed that the PEG, they could see the thermal, that is melting point is retained at the same position. So this is how they do the interpretation of the results with respect to the DSC. So there are some limitations, of course. With respect to our subject, we are learning the limitations. So hydrolytic degradation process cannot be controlled in a DSC experiment. Maybe there is some water molecule. Okay. So what happens? The hydrolysis is aggravated in the presence of temperature, because differential scanning colorimetry is a procedure which is carried out from the low to higher temperature. It's a thermal procedure. So hydrolysis is one of the degradation procedure which might happen. As such, when I mix the drug and excipient, you may not see any kind of hydrolysis happening. But because of the analytical procedure, what is the analytical procedure? We are subjecting that mixture to the DSC, and because of that procedure, the unnecessary degradation is happening. That is, interaction is happening, which is like not feasible for us to use it for the interpretation purpose. So hydrolytic degradation, when the drug has moisture and there is a chance of tendency of aggravated in the presence of temperature, then you cannot go with this technique. And this evaluation, as I was telling, the range generally they use, if you observe carefully in the previous graph, look at this graph, the scale. You can start from the lowest of 0 degree also, depending on your, for example, PEG in this case, they have used the melting point, they would have got from literature, it is 60 degree. So I should be fixing the lowest temperature based on the lowest melting point of your excipient, which is having the lowest. For example, some of the excipient might have 50 degree, or some might have 40 degree as a melting point. then I need to run the DSC from that low temperature to the high temperature, and high is usually up to 300. Why that 300 means generally the high temperature is based on the highest melting point. For example, paracetamol is 170. So I need to run up to at least 200. I cannot run up to 150 because I will be missing this point if I run up to 150. So the temperature range is decided based on the melting point of the ingredients which we are used for the test purpose. So now generally the normal procedure says what? It is run between 0 to 1 second. It is run between 0 to 300 degree. This is the normal range up from 0 to 300 degree, and that range, within that you can fix your own range. Okay, and the increase in temperature increases the reaction kinetics. That's what I was telling you. Any reaction, any unwanted reaction between the drug and excipient, or unwanted reaction happening between the drug and the environmental factor, drug and the moisture, drug and the pH around it, or drug and the temperature. So that is individual with respect to API, or the interaction may be between the drug and excipient, which is also dependent on the environmental factor. So one of the factor is temperature. When I know there is a temperature effect, it can result in the change in the physicochemical properties. Then what I have to do is I cannot go with the DSC results because it might be giving us the wrong result. The unwanted interaction might pop up because of the experiment, that is analytical procedure, because that procedure is running between our temperature 0 to 300 degrees centigrade. So I should not go with this technique. Then this technique cannot be used. It is not recommended. But of course, if none of these drawbacks are there, it's one of the best technique which helps us to identify the drug excipient interaction. So that's the reason they have gone through another technique called as high sensitive DSC, which is used to evaluate the drug excipient interaction using stepwise temperature program. This is the next slightly modified version of the basic DSC technique, where they could avoid this kind of unwanted reaction happening in the presence of temperature, where like in bits and pieces, stepwise the drug is exposed to the particular temperature. Anyway, it is just an additional information for you. So that's about the DSC. Let's go to the next one. Any doubt you have regarding the DSC? Hope everyone written what is DSC full form? Differential scanning colorimetry. All of you written that. And what is the thing to be
Yes.
remembered is the thermogram representation of the DSC should be remembered. Thermogram. The data, whatever you get after the analysis, is represented by with the suitable thermogram. And what is x-axis contains, what y-axis contains, parameter you should remember. Fine. So let's quickly learn about few more techniques. This is also has important applications called as TGA, thermogravimetric analysis. And if at all you have Latchman textbook, anyone have kept Latchman textbook at home? Leon Latchman? Have you
No,
purchased
ma'am.
anyone? No, by chance during your UG course?
No, ma'am.
Okay, fine. If you don't have, don't worry. That book contains all this information. Whatever I am telling, no, I would have taken from different textbooks. Okay, that's not a that's not mattering us here. But I'm just giving you, by chance if you have Lashma textbook at home, no, even all these informations you can get. Pre-formulation chapter only is there in the textbook, where you get all some of the points, whatever I'm discussing, no, you can get it in that textbook also. That is when you come back to college expecting the government may be taking decisions starting in the November, as per the news I'm talking. Okay, so I'm not very sure. I'm not telling it's from November. As per the news which I was going through yesterday, central government has given permission to start the degrees. Okay, UG and the PG from November. So let's see what our state government will take the decision. So happen to come to college, first thing please contact me and get collect the textbook information so that I'll ask you to refer which book, and you can start preparing yourself. So TGA is the thermogravimetric analysis, another type of thermal analysis. We are almost we are discussing about the thermal analytical technique used for identifying the drug-recipient interaction. Another in that one was completed is thermogravimetric analysis. It is almost like your DSC, but instead of measuring the endothermic peak and exothermic peak, okay, that is change in the endotherm exotherm process happening. Here it measures the change in the sample weight. Measures the change in sample weight as function of time. So if I ask you to plot the graph, what will be the graphical representation? What will be the thermogram in this case? Yes, if I ask you to plot the graph, what will be the graph you are going to plot? So Chitra,
Ma'am,
what will be your graph plotting? Between what and what you are plotting? What will be x-axis? What will be
time,
y-axis?
time and the sample weight.
Okay, that is your guess. Okay, fine. What about Tejaswini? Do you have any addition to that answer? You want to tell anything else, or it is correct?
Sample and temperature, ma'am.
Sorry, sample, weight, and temperature. Temperature you are telling? Okay. So
Yes,
any other
ma'am.
guess like this? Soundarya, KV, you have any other thing? Suchitra told time and weight of sample, and Tejaswini is
Sample
telling
on y-axis and temperature x-axis.
it's okay. So I want you guys to think. See, when you think, no, you will never forget. When you try to analyze from your side and try to imagine certain things and understand the concept, you'll never forget that concept. Fine, it's right or wrong, don't worry. So no other answer other than whatever those two have told. Okay. So it is percentage weight. Look at the first graph. You can mute yourself. So don't look at this. Don't look at this. Just look at the first one. One second. Don't look at this graph. This is DSC graph. You might get confused. This graph you look, this is the TGA graph. So it's a temperature. So both your answers are half correct. Suchitra said time, I think, and Tejaswini said temperature. I think Tejaswini's was the right answer. Did you say percentage weight, Tejaswini, to in the y-axis?
Yes, ma'am.
Okay, fine. So this is what I want you guys to imagine, understand and imagine and see now when you actually see the result, you'll never forget it. So it's the temperature and the percentage weight remaining. That's what they do it in the thermal, that is gravimetric analysis. So similar to your PSC only, subjected to the higher temperature. So what happens is it is restricted to the loss in mass during the process. Mainly, it deals with the weight. So that is loss in mass happens during the process, and that process is what is a thermal procedure, and that helps us to understand any desolvation, solvation, and decomposition. Means any moisture is absorbed or any moisture is removed, anything, any change happening to the sample. Okay, after subjecting, you'll understand what was the change happened to the sample. I have stored the sample at particular environment, and I want to see what has happened to that sample. So whether the moisture is absorbed or the moisture is removed, all this information or any even the decomposition can result in change in the weight. So basically, it is loss in mass, change in mass, which happens during the procedure, and that gives us some information with respect to the solvation, desolvation, and the decomposition. And in pre-formulation, its a major application of TGA is it is used in quantitative determination of the total volatile content of a solid. So the major application is with respect to that. It helps us to, for example, I have a sample and I know there's some volatile component in that. So that gives me idea what may be the volatile content. One of the application I'm telling you. It's not exclusively used for determining the volatile content. No, I'm not telling that. But it is mainly used to identify the if any volatile content is there, because during when you're subject to the thermal procedure, the volatile content will escape and that will result in change in the weight. Same thing with the moisture is present and the moisture is getting escaped during the procedure, there will be change in the weight. So anything happening with respect to loss of any content in the sample which affects the weight of the sample, and that change in the weight with respect to the loss of moisture or the loss of volatile content, all that can be easily identified with the TG. So this TGA records under identical conditions aid in the interpretation of thermal processes. This is a part of this procedure. So identical condition in the sense I should not be changing the conditions between one sample to another sample. The condition should be retained, maybe with respect to humidity, maybe with respect to whatever change, anything which can affect the procedure because it's the weight of the sample. No, so you should be very careful, because even small amount of addition of water can result in the change in the weight. So all this depends on the sample size, particle size, heating rate, sample atmosphere, sample preparation, sample homogeneity. So like this n number of factors can affect your result. So you should be very careful because it's based on the weight. We are going to assess the interpretation, and this is how the graphical representation. So just look at the graph. Is it clear for you? Can you see? Observe there are three lines. You can see the graph?
Yes, ma'am.
Yes, ma'am.
Three samples. Imagine there are three samples. One is the anhydrous form of some sample. Other one is the anhydrous dihydrated form mixture. Okay. And next one is pure dihydrated form. It's just a comparison. So look at that how the line is changing the weight. For example, the first case, anhydrous form. Anhydrous form means there is no moisture content. It's free of the moisture. So the line smoothly runs from beginning and then till the end of the procedure. Because there is no change in the weight happening. They could not see any change in the weight because there is no component which was getting removed during the procedure. Maybe volatile component or the moisture. But look at the second one. It is a dihydrate which is present in the 10:1 in the sense 10 part of anhydrate mixed with the 1 part of dihydrate. Okay. So anhydrous part is more, but the 1 part is only dihydrate. But still it's 1 part dihydrate. No, there is a water content. So obviously due to the temperature, this temperature increase, the water content will be removed and the weight will be changed. So that's why you can see the change in the weight. The dip, can you see the dip here at this position? So there is slight, it's not running smoothly, suddenly there is a dip. That indicates change in the weight. And look at the last example, it's only the dihydrate form which is not mixed with the anhydrous form. So there is a drastic reduction in the weight. So this weight values, whatever you're seeing in the percentage, maybe the weight is reduced from 100%, it is reduced to almost to the 90%, almost to the 90%. Means this is how the graphical representation helps us to understand the effect of temperature on the change in the weight of the sample. This can also be one of the analytical technique which can be used to identify the drug interaction. Same that at the bottom, if at all you are out of curiosity, if you want to know what is that at the bottom of this first graph, this is the DSC graph. So this is the DSC graph. Why I was little hesitating to show you, because this is reverse. Whatever graph we could see previously, one second. Here, the endotherm peaks are towards downside. It's easy for me to imagine always endo means something dipping down. So, but here the graphical representation is reverse, means endotherm peaks are shown upward side. So you should not get confused. That's the reason I was avoiding that. But still, it is just graph is made to plot in the upper direction. That's all. Otherwise, it's the same DSC graph. We can imagine the ulta, the reverse of it. So whatever the sample was understood by the TGA technique here, that is based on the weight loss. Same samples were also subjected to the DSE, and there also they could see this variation happen. Okay, so that's the advantage of this analytical techniques. So any variation happening with respect to the drug excipient interaction can be easily identified, and even the loss in the moisture, okay, was also identified even in the case of DSC curve also. Can you see the extra curve appearing? Okay, so that's is not visible in this case or even in the second line. So this is the advantage of, if at all you have more analytical technique with you and you want to do all and then interpret the result, it gives a better interpretation than just with the DSC or just with the TGA. You may not able to conclude many times, but with the supporting other analytical technique, you get a better interpretation. So second thermal method, you are clear now? So any doubt? Ashita?
No, ma'am, it's clear.
Can you just tell me the full form of DSC, dear?
Uh, Differential scanning calorimetry.
Yes, fine. What is TGA?
TGA is gravi. No, ma'am, wait. The
TGA.
thermogravimetry analysis.
Fine. So I want you guys to at least know this basics. Though I'm not expecting you to learn, as I told, this is not analysis subject. But in analysis, when you happen to study this equipment in detail, give your 100%. So it becomes easy for you to understand this subject. So I'm winding up the class now. Sir will be taking your class next hour. So any doubts you can ask, because I can go with next topic, but I doubt I can complete. So anyway, so any doubt? No doubts, right? Let me wind up. I did not find Trupti. Trupti is there? No, Trupti is not there. Saundarya SK, Suchitra, Chandana, Saundarya, KV, Ashita Verma, Asha Vista. Only these are present. See, your attendance are really mandatory. Please don't ignore, neglect that component. So try to attend all the classes, because it's from home you're doing, right? Attending the class. So should not be any problem. Okay, then see you tomorrow with the continuation of the same topic. And you can contact for any doubt. You can contact. Please parallelly start reading. The online sources you can utilize. I'll tell you how to do that. Kindly search for an article which talks about this topic. Research review articles. I'm talking drug excipient interaction review article. You search. You get the articles which is already been published in the journals. You can use that as source of material, study material for your purpose. So let's not wait for the things to come back to normal. Let's start preparation from our side in the possible way. Okay, so all of you can what you can do is just search drug excipient interaction in pharmaceutical industry review articles. The key search is so important. Whatever the key you decide for searching, no, based on that only you're going to get the refined results. So you should, even that is also one of the important thing you need to learn when you go with the next year with the research, or not only then second year, now itself, anything you want to get it from the internet, you should be confident all the informations are not authentic in the internet. Don't go with the ready-made ppts in your internet source. So okay, you can always trust on published articles. Those are the articles which would have been published in the particular journal. I recommend only those as a authentic information. So search, and once you get any article, you can contact me, show me that article, and I will confirm whether to refer that or not. Okay, enough. Sir will be waiting, I think. Let him take his class. Okay then.